James Webb has been looking deeper into the universe than ever before, and some of its latest observations are shaking the foundations of cosmology. Galaxies forming too early, stars appearing where they shouldn't. Could this mean the Big Bang never happened as we thought? Today, we're diving into the discovery that's challenging everything we know about the universe. The promise of the James Webb Space Telescope. When humanity first turned its eyes to the sky, it was filled with wonder, curiosity, and the desire to understand where we come from and what the universe is. Generations of scientists, engineers, and dreamers worked tirelessly to create instruments capable of piercing the veil of space and time, and among them, the Hubble Space Telescope became the icon of cosmic discovery. Hubble revolutionized our understanding of the cosmos, revealing galaxies, nebulae, and phenomena that were previously unimaginable. Yet it still left vast portions of the universe hidden, veiled in darkness and infrared light beyond its reach. The James Webb Space Telescope, or JWST, was born from this desire to push further, to look deeper, to see further back than anything before. It was designed not merely as a successor to Hubble, but as a radical leap forward in humanity's ability to observe the universe. Unlike Hubble, which primarily works in visible and ultraviolet light, JWST is an infrared observatory, capable of detecting the faint heat of the first galaxies forming over 13 billion years ago. By capturing infrared light, JWST can see through cosmic dust clouds, which obscure much of the universe from visible light telescopes, revealing galaxies and stars in their earliest stages of formation, long before humans could even imagine their existence. The mission behind JWST is monumental. It is tasked with peering back 13.5 billion years, close to the dawn of time itself, in order to uncover the origins of galaxies, stars, and ultimately the universe as we know it. It was conceived to answer some of the most fundamental questions of cosmology, to test the predictions of the Big Bang theory, and to observe the very first moments of cosmic inflation. Its design, technological innovations, and scientific purpose all converge into a single powerful tool capable of reshaping our understanding of everything. The technology of JWST is nothing short of extraordinary, reflecting decades of planning, testing, and refinement. Its optics are centered around a massive 6.5-meter mirror composed of 18 hexagonal segments, each coated in ultra-thin gold to optimize the reflection of infrared light. Gold was chosen because it is highly reflective in the infrared spectrum, allowing the telescope to detect the faintest heat signatures from the earliest galaxies, billions of light years away. Every segment of the mirror was crafted with extreme precision, polished to near perfection, and engineered to withstand the cold vacuum of space without warping. JWST's infrared sensors can detect wavelengths invisible to the human eye, enabling it to see the universe in a way no previous telescope could. Surrounding the telescope is a sunshield the size of a tennis court, made of 5 layers of ultra-thin, heat-resistant material. This sunshield protects the telescope from the sun, Earth, and Moon, keeping it incredibly cold and stable, which is essential because infrared instruments can be overwhelmed by even tiny amounts of heat. The sunshield allows JWST to reach temperatures below -220 degrees Celsius, ensuring that its instruments can detect the faintest signals from the first galaxies without interference. Compared to Hubble, which revolutionized astronomy in visible light, JWST is more sensitive by orders of magnitude in the infrared, capable of observing objects that are both fainter and further away, effectively extending the reach of human vision to the edge of the observable universe. The combination of gold-coated mirrors, advanced infrared detectors, and the enormous sunshield creates a telescope that is both a technological marvel and a window into the earliest moments of cosmic history. The scientific goal of JWST is as ambitious as its engineering. It was designed to map the formation of the first stars and galaxies, to observe the processes that led to the universe's large-scale structure, and to gather data that could either confirm or challenge the predictions of the Big Bang theory. By studying galaxies as they formed in the universe's infancy, Scientists hope to better understand how stars accumulate, how galaxies grow, and how chemical elements essential for life are distributed across space. JWST is expected to reveal galaxies that existed only a few 100 million years after the universe began, capturing light that has traveled across more than 13 billion years of space and time. Its observations provide not just static images, but data that can be analyzed to determine the mass, age, chemical composition, and star formation rates of these ancient galaxies. In doing so, JWST allows scientists to test the models of cosmic evolution with unprecedented precision. If galaxies are forming differently than predicted, if they appear earlier or more developed than models suggest, it could mean that our understanding of the Big Bang, cosmic inflation, or early galaxy formation needs to be revised. The telescope was, in theory, supposed to confirm the textbook story of the universe, showing galaxies that align with the predictions of existing cosmological models. Instead, the first images and discoveries suggest a universe that is far more mature, more structured, and more complex in its earlier stages than scientists anticipated, challenging fundamental assumptions about the pace and process of cosmic evolution. Imagine a universe that was once considered dark, empty, and primitive, suddenly revealed in its full glory, brimming with massive, fully formed galaxies that existed when the universe was still a fraction of its current age. Each image from JWST is a time machine, transporting viewers across billions of years to moments that were once purely theoretical. Scientists and engineers built this telescope to confirm a story that has guided cosmology for nearly a century, rooted in the Big Bang theory and the subsequent evolution of the cosmos. Yet the universe, as JWST now shows, seems eager to tell a different tale, a tale of galaxies forming and maturing far more quickly than anticipated, a tale of complexity emerging almost immediately after the universe's birth. The Big Bang theory in a nutshell. Scientists have spent decades trying to understand where the universe came from and how it grew into the vast cosmos we see today. According to the Big Bang theory, the universe began about 13.8 billion years ago. At that first moment, it was not like anything we can truly imagine. The universe was smaller than an atom, unimaginably hot and incredibly dense. All the matter, energy, space, and even time itself were packed together in one tiny point. It was a singular beginning where everything that exists now was compressed into a state of extreme heat and pressure. Imagine a fireball so hot that atoms could not even form, a place where light itself could not travel freely because everything was so tightly packed. This was the universe at the very beginning, and it was about to change in ways that would set the stage for all of cosmic history. From this tiny, hot, dense state, the universe began to expand rapidly. Scientists expected this expansion to cool the universe over time, allowing the first simple particles to form. As the universe stretched, protons, neutrons, and electrons began to appear. Eventually, these particles combined to make the first atoms, mostly hydrogen and helium. This process of cooling and atom formation was slow on cosmic scales, but it was crucial because it prepared the universe for the next stage, the formation of stars and galaxies. In the very first few 100 million years, the universe was dark. There were no stars to light it up, no galaxies to shape its structure. It was a dark sea of gas, quietly spreading and cooling, waiting for gravity to pull it together into the first lumps of matter that would eventually become galaxies. Scientists expected that the very first galaxies would be extremely small compared to the massive galaxies we see today. They should be rare, scattered across the vast darkness of the early universe, forming only in a few lucky spots where matter had clumped together enough. These early galaxies would not yet have complex structures. They would be primitive, made mostly of hydrogen and helium, and their stars would be young, bright, and simple. Heavy elements like carbon, oxygen, and iron, which are essential for planets and life, would not yet exist in these first galaxies. Stars had to live and die first to create these elements, and there simply had not been enough time. Therefore, Scientists expected the early universe to be filled with simple, small galaxies, slowly forming stars in a quiet and orderly way, with space between them largely empty and dark. To study this early universe, scientists rely on the cosmic microwave background, or CMB. The CMB is often called the baby picture of the universe because it captures the universe at just 380,000 years old, a time before stars or galaxies existed. At this stage, the universe had cooled enough for light to travel freely, leaving behind a faint glow that still fills space today. Scientists can measure tiny variations in this glow, small ripples that indicate where matter was slightly denser. These ripples are important because they show where gravity would eventually pull gas together to form the first galaxies. In other words, the CMB is like a map of the universe's earliest blueprint. By studying it, scientists expected to predict where the first galaxies would appear, how big they might be, and how many there should be. This blueprint guided every expectation about the early universe. According to these predictions, when scientists looked back in time with telescopes, they expected to see a universe that was calm and slow to develop. Early galaxies should appear tiny and faint because they had only just begun forming stars. They would be scattered sparsely, not grouped into large clusters. Their stars would be young and simple, shining with the light of hydrogen and helium. There would be no heavy metals, no complex structures, and no fully formed galactic shapes like the spirals or ellipticals we see today. The universe was expected to look like a quiet, almost empty place, gradually coming to life as gravity slowly assembled matter into galaxies. These expectations set the standard for what telescopes like the James Webb Space Telescope were designed to find. Scientists built their models based on this vision of the universe, and they predicted exactly what the first glimpses of ancient galaxies would look like. The idea of the early universe being small, rare, and primitive is not just a theory. It is based on precise calculations of physics, gravity, and the expansion of space. Scientists calculated how matter would clump, how hydrogen and helium would cool, and how stars would ignite in the first galaxies. They used the CMB to understand the starting conditions of the universe and to predict how structures would grow over time. These calculations told scientists that the first galaxies would be faint, scattered, and simple, forming slowly over hundreds of millions of years. It was a universe of potential, quiet and small, waiting for stars to ignite and galaxies to assemble. This expectation was the baseline against which every observation of the early universe would be measured. Every telescope aimed at the distant cosmos, including JWST, was designed to confirm or challenge these predictions. Predictions relevant to JWST. When scientists imagined what the James Webb Space Telescope would find, they built their expectations on decades of research about the early universe. According to the models derived from the Big Bang theory and the cosmic microwave background, the first galaxies that formed after the universe's birth were expected to be very small and very faint. In the earliest epochs, galaxies were not the massive, bright, and structured systems we see today. They were low in mass, composed mostly of gas with only a few stars lighting up their clouds. These early galaxies were delicate, fragile structures, still forming, still collecting their stars and matter. Because they had such low mass, their gravitational pull was weak, and this meant that they could only hold on to small amounts of gas, forming just a few stars at a time. Scientists expected these galaxies to be scattered across the vast darkness of the early universe, isolated in space, and difficult to detect, even with the most powerful telescopes. The faint glow of their few stars would have been the only evidence of their existence, barely visible across billions of light years. These faint early galaxies were thought to be the building blocks of the universe, slowly merging and growing over hundreds of millions of years to eventually form the massive systems that populate the cosmos today. Their low brightness was directly tied to their low mass, and this faint light was what JWST was designed to detect. stretching its powerful infrared vision across the universe to catch the first photons emitted by these tiny galactic pioneers. In addition to being faint and low in mass, these early galaxies were expected to have very low metallicity. In astronomy, metals are all elements heavier than hydrogen and helium. At the very beginning of the universe, there were no metals because stars had not yet had time to create them. Heavy elements are formed inside stars and spread through space when stars die in supernova explosions. Since the first galaxies were just forming, their stars would not have lived long enough to produce metals or to enrich the surrounding gas. As a result, the earliest galaxies were expected to be made almost entirely of hydrogen and helium, simple and primitive in composition. Scientists predicted that any metals present would be extremely rare, just a tiny trace here and there, as the universe was still in its infancy. This low metallicity had consequences for the type of stars that could form. The first stars, known as population 3 stars, were thought to be massive, bright, and short-lived, forming only from hydrogen and helium gas without the influence of heavier elements. These stars would burn quickly, live for only a few million years, and explode in supernovae, beginning the slow process of enriching the universe with metals. Because metals affect how gas cools and condenses into stars, their absence meant that early galaxies would have a very different structure compared to galaxies formed later. JWST was designed to study this low metallicity environment, capturing both the faint light of the first stars and the early chemical signatures of these primitive galaxies, providing a glimpse into a universe still learning to form complex structures. The timeline for the first stars was also part of the predictions that JWST was meant to test. According to scientists' models, the first stars did not form immediately after the Big Bang. After the universe expanded from its hot, dense beginning, it took hundreds of millions of years for gas clouds to cool, condense, and begin the process of star formation. The first stars were expected to form around 400 million years after the Big Bang, at a time when the universe was still young but beginning to light up. These first stars were essential for transforming the early universe, as they produced the energy and heavier elements necessary to allow later generations of stars and galaxies to form. The period before 400 million years after the Big Bang was a dark age, when the universe was filled with diffuse gas and no stars or galaxies had yet ignited to light up the cosmos. This gap in time was significant because it defined the pace of cosmic evolution, setting expectations for when JWST might detect the first signs of starlight from distant galaxies. Astronomers predicted that JWST would find galaxies appearing gradually, with stars forming in small numbers at first, and increasing over time, slowly building the complex systems we see today. Because of the faintness, low mass, and low metallicity of these early galaxies, detecting them was no easy task. Scientists knew that the light from these galaxies would have traveled for more than 13 billion years to reach us. As the universe expanded, this light was stretched into longer wavelengths, shifting from visible light into the infrared. JWST was built specifically to capture this infrared light, allowing astronomers to see objects that had been invisible to earlier telescopes. Its instruments could measure the brightness, mass, and composition of these ancient galaxies, providing data to compare against the predictions of low mass and low metallicity. Every photon detected by JWST from these faint early galaxies would be a confirmation of the expected timeline of cosmic evolution. By studying these faint objects, scientists could test whether galaxies indeed formed slowly and gradually after 400 million years, and whether their composition matched the predicted low metallicity expected in the universe's first generations of stars. The predicted properties of early galaxies were not just theoretical ideas. They were grounded in detailed physical models of the universe. Scientists calculated how gas cooled under the influence of gravity, how stars would ignite in the earliest clouds, and how galaxies would grow over time. Low mass meant weak gravity, limiting the number of stars forming in each galaxy. Low metallicity meant that gas cooled slowly, so star formation was inefficient at first. These factors combined to predict a universe filled with tiny, dim galaxies sparsely scattered across space, with only the occasional burst of bright starlight from the rare massive population 3 star. JWST's mission was designed to detect this first generation of galaxies, observing the faint glow of their stars and the primitive composition of their gas. The telescope's instruments were calibrated to capture these specific signals, making it possible to test whether the early universe matched these long-held predictions. If these galaxies are faint, low mass, and low metallicity, it confirms that the universe evolved according to expectations. If they are different, brighter, larger, or more chemically enriched, it suggests that galaxies formed faster or in ways scientists had not predicted. The 400 million year mark for the first stars is a key point in this timeline. It marks the expected transition from the cosmic dark ages to a universe illuminated by starlight. Detecting stars forming around this time would confirm the predicted pace of cosmic evolution and provide the first direct evidence of the universe's early structures. JWST's ability to measure both the faint light and the composition of these early galaxies allows astronomers to directly test these predictions, offering a unique opportunity to compare theory with observation. The faintness of early galaxies also has implications for how many galaxies JWST was expected to detect. Because they were low in mass, these galaxies would contain relatively few stars, making them dim and difficult to spot. They would be scattered sparsely, requiring JWST to observe carefully selected regions of the sky to maximize the chance of detection. The telescope's sensitivity in the infrared allows it to gather light from billions of years ago, revealing these faint galaxies one by one. Each detection provides data on how early stars formed, how gas cooled, and how galaxies began their long journey to become the large systems we see in the modern universe. Low metallicity also influences star formation. Without heavier elements, gas clouds cool more slowly, delaying the ignition of stars. This means early galaxies would not only be faint but also slow-growing, with stars forming gradually over millions of years. JWST is capable of measuring these subtle differences, capturing the faint light and faint chemical signatures that reveal the primitive state of the universe. The first stars forming around 400 million years after the Big Bang were expected to play a crucial role in shaping the universe's evolution. These stars would be massive, burning brightly and dying quickly, producing the first heavy elements needed for future generations of stars and planets. Their light would begin to ionize the surrounding gas, slowly transforming the neutral hydrogen of the cosmic dark ages into a glowing, transparent universe. JWST was expected to detect the faint signals of these first stars indirectly, through the galaxies they formed and the light they emitted. But why does this matter? Why this matters? You see, every prediction scientists make about the early universe acts like a marker, a benchmark that shows how the universe should behave. The first galaxies, small and faint, made of mostly hydrogen and helium, forming hundreds of millions of years after the Big Bang, were expected to follow a pattern that fits the standard model of cosmology. This model is the story scientists tell about the universe's birth, growth, and evolution. Each benchmark is a checkpoint, a point where observations can be compared to predictions. If the galaxies appear the way scientists expect, if they form at the predicted time with the predicted size, mass, and chemical composition, it means the models are holding true. Every faint galaxy, every early star that matches the prediction, reinforces the story of the universe as it was imagined. The benchmarks are like signs along a road. If the signs line up, the journey follows the expected path. Scientists can look at these galaxies and know that the universe is unfolding as predicted. A quiet, orderly process that started 13.8 billion years ago and continues across the cosmos. These benchmarks are critical because they set the limits of what is possible. They define the rules that the universe is expected to follow. Early galaxies are not just dots in the sky. They are evidence of the universe following the script written by the standard cosmological model. If these galaxies are faint, low mass, and low in metals, the universe is acting exactly as it should. If they appear earlier than expected, larger than predicted, or chemically richer than models suggest, it signals that something in the story is wrong. The benchmarks are tests. They are the points of reference that determine whether the universe's evolution matches the script, or whether there are surprises hiding in the darkness. Every observation of a distant galaxy, every photon collected by JWST from billions of years ago, acts as a check against these predictions. The first stars, forming around 400 million years after the Big Bang, are another benchmark. They mark the transition from darkness to light, the moment when the universe began to illuminate itself. If stars appear at the expected time, the universe is behaving as the models suggest. If stars appear too early or too late, the timeline of cosmic evolution must be questioned. These benchmarks are more than numbers or theoretical predictions. They are the standard against which the entire story of the universe is measured. The faint, low-mass galaxies and the timing of the first stars are reference points that the standard model depends on. The standard cosmological model is built around these predictions, and everything else flows from them. Galaxy formation, star formation, the spread of metals, the structure of the universe, all rely on the idea that these early galaxies and stars behave in predictable ways. If they do, the story holds together. If they don't, the framework starts to crumble. This is why every observation matters. JWST does not just take pretty pictures. It collects evidence that tests these benchmarks. Each image of a faint galaxy, each spectrum showing low metallicity, each detection of stars forming at the expected time is a piece of the puzzle that either confirms or challenges the story written in the standard model. If these predictions fail, the standard cosmological model faces a real challenge. The faint, low-mass galaxies expected in the early universe are not just numbers in a simulation. They are the foundation of the timeline of cosmic evolution. Their mass, brightness, and composition are tied to how matter and energy interact, how galaxies merge and grow, and how stars form and die. The timing of the first stars is linked to the cooling of gas and the ignition of nuclear fusion. If observations show that galaxies formed faster, stars appeared earlier, or metals spread more quickly, it could mean that the universe evolved in ways the standard model does not account for. Benchmarks are the proof points. If they fail, the model loses its anchor. Scientists would have to re-examine the assumptions that underpin every calculation, every prediction, and every understanding of the early universe. The stakes are enormous because these benchmarks are not minor details. They define the structure, the growth, and the timing of the universe itself. Every early galaxy observed is a test of these benchmarks. If the galaxy is brighter than expected, it signals faster star formation or higher mass. If it has more metals than predicted, it hints at processes in the early universe that models missed. If the first stars appear before the predicted 400 million year mark, the timeline shifts and the story of cosmic evolution changes. Each benchmark that fails acts like a warning sign, showing that the standard model may not fully describe reality. The benchmarks are not just for scientists. They are the measuring sticks that allow humanity to see whether the universe is unfolding as predicted or whether it has secrets waiting to be discovered. JWST's mission focuses directly on these points, capturing the earliest light, the first stars, and the faintest galaxies, each one a checkpoint on the cosmic map. These benchmarks are essential because they are the connection between theory and reality. Without them, predictions would have no way to be tested. The faint galaxies and the first stars serve as the reality check. Scientists can imagine how the universe began, simulate its growth, and calculate its evolution, but these predictions mean little without the benchmarks. Observing the universe through JWST provides the evidence needed to compare theory with reality. Every galaxy, every star, every measurement tests whether the universe behaves as expected, or whether the story needs to be rewritten. The faint early galaxies are not just points of light. They are proof of how matter gathered, how stars began to shine, and how the universe transitioned from darkness to the complex cosmos we see today. The first stars, forming around 400 million years after the Big Bang, mark the moment the universe turned on its first lights, a benchmark of timing that cannot be ignored. If the benchmarks fail, the consequences are profound. The standard cosmological model is the framework for nearly all of modern astronomy. It explains the formation of galaxies, the evolution of stars, the distribution of elements, and the structure of the universe on the largest scales. Each benchmark that does not align with observations signals a crack in that framework. A universe that does not follow these benchmarks could indicate new physics, processes not included in current models, or a need to rethink the timing and mechanisms of cosmic evolution. The benchmarks are the measuring sticks, and JWST is the instrument that reads them. Faint, low-mass galaxies, low metallicity, and the first stars are the reference points that determine whether the standard cosmological model continues to hold or whether it must be challenged. The discovery that changed everything. When the James Webb Space Telescope opened its eyes to the deep universe for the first time, it captured images that no one could have expected. These were not just pictures of distant points of light. They were snapshots of the universe's infancy, showing galaxies that had formed in the first few 100 million years after the Big Bang. Scientists had prepared for faint, tiny, primitive galaxies scattered sparsely across space. Instead, JWST revealed a cosmos that was alive, bright, and bustling much earlier than anyone imagined. Each image was filled with hundreds of galaxies, more than the most optimistic models had predicted. These early galaxies were not the weak, fragile structures scientists expected. They were massive, glowing with stars and already well formed. Some of them shone with a brightness that rivaled galaxies we see in the nearby universe today. It was as if the universe had skipped its slow-growing phase and jumped straight into maturity. The sheer number of galaxies in these first deep-field images was staggering. Where astronomers expected a handful, JWST found dozens, hundreds, a universe teeming with young galaxies that were already enormous compared to what models suggested should be possible at that time. Each galaxy was a mystery, a puzzle piece that did not fit into the neat story scientists had been teaching for decades. The telescope revealed a universe that was not tentative, not primitive, not fragile, but already bold and full of light, only 200 to 300 million years after the Big Bang. These first snapshots went beyond simple images. They carried detailed information about the galaxy's shapes, sizes, and brightness. Scientists could measure the light from each galaxy and estimate how massive it was. The surprising truth quickly became clear. These galaxies were already massive, with stellar masses far higher than predicted. They contained stars in numbers and arrangements that models of early galaxy formation could not explain. According to textbooks, the first galaxies should have been small, faint, and slowly building their stars over hundreds of millions of years. Instead, JWST showed galaxies that were already well formed, with stars shining brightly, forming clusters, spirals, and shapes that suggested a level of organization thought impossible so early in the universe. The brightness of these galaxies alone challenged the expected timeline. Light traveling across billions of years arrived at JWST from galaxies that should not yet have had time to shine so brightly. The telescope's infrared eyes revealed structures that models had assumed would take much longer to form, showing that the universe had already moved far ahead of the predicted schedule. The implications of these early images stunned the scientific community. Every snapshot taken by JWST seemed to defy expectations. Galaxies were not scattered sparsely across the cosmic canvas. They were clustered, grouped, and surprisingly common. The universe, according to these pictures, was far more mature than anyone had imagined for its age. Astronomers had expected a slow, gradual build-up of galaxies, starting with tiny clumps of stars and gas, growing over hundreds of millions of years. Instead, the deep field images suggested that massive galaxies had already formed in remarkable numbers, lighting up the early universe with energy and stars. Each galaxy was like a glowing city, fully built, where scientists had only expected the outlines of construction sites. The sheer scale of these galaxies, combined with their brightness, suggested that star formation was happening at rates far beyond what models had allowed. JWST's early deep field images were not just surprising, they were revolutionary, revealing a universe that had progressed faster, bigger and brighter than anyone had thought possible. JWST's first glimpse into the universe's infancy did not just show individual galaxies, it revealed a pattern that hinted at widespread, rapid development. Galaxies appeared in clusters, indicating that the processes of star formation, gas collapse, and gravitational gathering were already in full swing. The density of galaxies in these first images far exceeded expectations, showing that the early universe was teeming with activity. Where scientists had predicted only small, rare galaxies forming slowly, JWST revealed hundreds of galaxies glowing brightly across the field of view, packed together in ways that models had never anticipated. These were galaxies forming stars at rates previously thought impossible so early in cosmic history, shining with the light of tens of billions of stars, even at a time when the universe was less than 2% of its current age. The images suggested that the cosmos was ready for its first grand structures far sooner than textbooks claimed. Perhaps the most striking aspect of JWST's early deep field images was the timeline implied by the observations. Some of the galaxies appeared fully formed only 200 to 300 million years after the Big Bang, a period that scientists had long believed would only contain the very first tiny, primitive galaxies. The models had predicted that at this age, galaxies would be small, faint, and chemically simple, with very few stars. JWST's images contradicted these expectations. The telescope showed galaxies that were already massive, bright, and seemingly organized. Star formation was already well underway, producing high stellar masses in an era when theory suggested the universe should still be in its infancy. It was as if the universe had skipped its slow-growing baby phase and moved straight into adolescence, with galaxies that were already large and luminous, shining brightly across the early cosmos. The early deep field images revealed a universe that was unexpectedly mature, forcing scientists to confront the possibility that the timeline of cosmic evolution might need to be rewritten. The first snapshots also provided astronomers with data that could be measured and analyzed. The number of galaxies, their brightness, and their apparent mass could all be compared to the predictions from theoretical models. Every galaxy in these images told a story about how quickly stars were forming, how matter was gathering, and how the universe's first structures were emerging. JWST's deep field images were not just pretty pictures. They were evidence that the early universe was far more active than anyone expected. The density of galaxies, their rapid formation, and the sheer scale of stellar mass all pointed to processes operating faster and more efficiently than standard models could account for. For the first time, astronomers had concrete visual proof that the earliest moments of the universe were filled with massive galaxies glowing brightly, a universe far from the small, faint and rare structures that textbooks had promised. Each galaxy in JWST's early deep field images carried with it clues about its history. The brightness indicated rapid star formation. The size suggested that matter had already clumped together efficiently. The distribution of galaxies across the images hinted at early clustering, a sign that gravity had already organized the universe into patterns. Scientists were able to measure these properties and see that they did not match predictions. Where theory expected small, primitive galaxies struggling to form their first stars, JWST revealed galaxies already massive and luminous, containing tens of billions of stars. This level of development, so early in cosmic history, challenged every expectation about how quickly the universe should have evolved. The early deep field images also revealed diversity in the early universe. Galaxies appeared in different shapes and sizes, some compact and bright, others stretched and elongated, suggesting that even in these first 200–300 million years, the processes of galaxy formation were varied and complex. The universe seemed to have explored multiple paths for creating galaxies almost immediately, instead of slowly following a single predictable model. The sheer variety of structures revealed by JWST indicated that the early universe was not a simple, uniform environment. Instead, it was already complex, rich with different types of galaxies, shining with stars, and organizing into patterns. Each snapshot was a window into this unexpected diversity, showing that even the earliest galaxies could be massive, luminous, and surprisingly structured. Specific examples from JWST. As James Webb Space Telescope started sending back its first detailed images, astronomers quickly identified a series of candidate galaxies that seemed to belong to the earliest epochs of the universe. These galaxies were measured at redshifts of around Z-13 to 15, meaning the light we see from them left these galaxies only 300 to 400 million years after the Big Bang. At this time, the universe was less than 3% of its current age, a place where theory had predicted only the tiniest, faintest, simplest galaxies could exist. But JWST's infrared vision revealed galaxies already glowing brightly, massive enough to stand out against the dark background of space. Each candidate galaxy was a puzzle, its light stretching across billions of years, carrying with it information about stars, gas, and the early processes of galaxy formation. Redshift Z-13 to 15 corresponds to extreme distances, pushing JWST to its limits, yet the telescope captured these signals with clarity, showing galaxies that had not only formed but were already substantial in mass and brightness. These were galaxies that, according to older models, simply should not exist yet. One of the most striking findings from these candidate galaxies was their estimated stellar mass. The galaxies discovered by JWST appeared to contain stellar masses far larger than theoretical models had allowed for the first few 100 million years of the universe. Models of early galaxy formation assumed that star formation would start slowly, with small amounts of gas coalescing into the first tiny stars and primitive galaxies. Building massive galaxies so quickly, within only 300 to 400 million years, seemed nearly impossible. Yet JWST's data suggested galaxies with stellar masses reaching billions of solar masses already in place at this early stage. Each galaxy contained far more stars than the models predicted could form in such a short time. It was as if the universe had been preparing these galaxies in secret, assembling them rapidly while models assumed a slow and gradual build-up. The fact that these galaxies were already massive and luminous only 300 to 400 million years after the Big Bang forced astronomers to reconsider how stars could form so efficiently, how gas could collapse so quickly, and how matter could assemble these large structures far earlier than expected. Another shocking discovery came from the chemical content of these early galaxies. Galaxies were showing surprisingly high amounts of metals, elements heavier than hydrogen and helium, in a period when models predicted the universe would still be almost entirely metal-poor. Metals are formed inside stars and spread when those stars die, so the earliest galaxies were expected to have very low metallicity. Yet JWST revealed galaxies whose stars and gas were already enriched with metals, a sign that previous generations of stars must have formed, lived, and died even earlier than the 300–400 million year window suggested. This implied that star formation, in the very first few 100 million years, was far more efficient and rapid than predicted. The presence of metals meant that the universe had already undergone a cycle of star formation and enrichment, a process scientists had assumed would take longer to produce observable chemical signatures. Galaxies at these extreme redshifts were not simple collections of hydrogen and helium. They were chemically complex, already showing signs of the life cycles of stars, hinting at a universe that had matured faster than anyone imagined. Each specific galaxy observed at these redshifts offered a story about the speed and scale of early cosmic evolution. Astronomers could measure the light coming from these galaxies, calculate their stellar mass, and analyze the chemical content through spectroscopy. The results repeatedly defied expectations. Where theory had predicted small, faint galaxies forming stars slowly, JWST showed large, luminous galaxies already in place, with stars formed in massive quantities and metals dispersed throughout their structure. These observations suggested that the first galaxies were assembling and evolving at rates that models had not accounted for. Every candidate galaxy at Z-1315 acted as a clue, showing that the early universe was more active, more energetic, and more chemically enriched than textbooks had assumed. The candidate galaxies at Z-1315 also revealed diversity in structure and brightness. Some appeared compact and intensely bright, while others were more diffuse yet still massive. This suggested multiple pathways for galaxy formation, even in these earliest times. Galaxies were not all forming in the same way, and the differences in brightness, shape, and chemical content hinted at complex processes shaping the universe almost immediately after the Big Bang. The variety of galaxies observed challenged the notion of a slow, uniform evolution and suggested that the universe was capable of producing a wide range of structures in a surprisingly short period. These early galaxies were more than just numbers and points of light. They represented real evidence that the universe's earliest phases were far more dynamic than predicted. Their existence at such high redshifts, combined with high stellar mass and unexpected metallicity, directly challenged the models that had guided astronomy for decades. Each candidate galaxy at Z-1315 showed that the universe had formed massive, complex systems far faster than anyone thought possible. JWST was not just confirming what scientists expected, it was revealing that the universe had been more prepared, more mature, and more efficient at building galaxies than the standard models allowed. The scientific reactions. When the first images and data from JWST began arriving, the scientific community was shocked. Astronomers stared at the screens, blinking in disbelief, seeing galaxies that, according to all predictions, should not exist yet. Massive, bright, well-formed galaxies glowing only 200 to 400 million years after the Big Bang forced scientists to question everything they thought they knew about the early universe. The reaction was immediate and intense. "These shouldn't exist yet," one astronomer reportedly said, summing up the astonishment that rippled through observatories and research centers across the world. Every discovery from JWST challenged the textbooks, forcing scientists to confront a universe that seemed far more prepared, far more active, and far more advanced in its early stages than anyone had imagined. Where the models predicted faint, tiny, primitive structures struggling to form stars slowly, JWST revealed galaxies already teeming with activity, shining brightly across the early cosmos. The images were undeniable, and the reaction was raw. The universe was moving faster than the story scientists had written. The astonishment went beyond surprise. It sparked a deep, urgent debate among astronomers and cosmologists. Some argued that these discoveries could point to flaws in the standard Big Bang model itself, suggesting that the timeline of cosmic evolution might need a radical rethink. Others believed that the Big Bang theory could still hold, but that the models used to predict early galaxy formation needed significant adjustments. Perhaps the physics of star formation, gas collapse, and chemical enrichment in the early universe were more efficient than the simulations had accounted for. Some suggested that unknown processes, maybe faster cooling of gas or more rapid merging of early clumps, could explain the unexpectedly massive galaxies. The debate was heated, spanning conferences, preprint papers, and informal discussions, all centered on a simple but profound question. Had JWST uncovered a universe that defied the Big Bang? Or had it simply revealed that the models used to describe the first few 100 million years were incomplete? Amid the discussion, the imagery from JWST carried a cinematic weight that words could hardly capture. The galaxies it revealed were not small points of light lost in darkness. They were glowing, bustling and structured, already performing the cosmic dance that scientists had expected only much later. The telescope seemed to be whispering a different story, one in which the universe had skipped slow steps and built massive systems far sooner than predicted. Scientists began to describe the images in metaphors that captured this shock. The universe was ready for dinner, but according to our textbooks, it was still in the womb. This phrase quickly spread among astronomers and journalists alike because it captured the tension between observation and expectation. The cosmos, it seemed, had grown up faster than the human story of its birth allowed, presenting a reality that was richer, brighter, and more surprising than theory had imagined. The reactions were not just about numbers or measurements, they were emotional. Astronomers and cosmologists, many of whom had spent decades developing models of early galaxy formation, were forced to confront the unexpected. Models predicting faint, small, primitive galaxies had been considered reliable, built on decades of observations, simulations, and theoretical work. To see galaxies with stellar masses far exceeding those predictions, glowing brightly with high metal content, was like watching a story unfold in front of them that had been written in a completely different language. Some scientists felt excitement and exhilaration, recognizing that the universe was giving them a chance to learn something entirely new. Others felt confusion and unease, realizing that some of the most basic assumptions about the first few 100 million years of cosmic history might need reconsideration. The feeling was universal. The cosmos was teaching lessons no one had expected. The debate over what these galaxies meant for the Big Bang itself was unavoidable. On one side, some astronomers asked whether the discoveries could imply a need to rethink the timeline of cosmic expansion, suggesting that if massive galaxies existed so early, the universe might have evolved faster than theory predicted. On the other side, many argued that the Big Bang itself remained robust, that these early galaxies did not overthrow the foundation of the theory, but merely indicated that the processes of galaxy formation were more efficient than models had allowed. Discussions considered the role of dark matter, the speed of star formation, and the physics of gas collapse. Could early stars have formed more quickly? Could galaxies merge faster than simulations suggested? Could unseen factors accelerate the creation of metals in the first stars? These questions dominated meetings, emails, and journal articles as the community struggled to reconcile theory with the extraordinary images JWST provided. Every image of a massive glowing galaxy at redshift Z-1315 represented a direct challenge to expectations, and every discussion, debate, and analysis carried the weight of rewriting the story of the early universe. The metaphor of the universe being ready for dinner while still in the womb perfectly captured the dissonance between observation and expectation. The universe appeared mature, luminous, and complex, yet theory predicted it should have been tiny, faint, and simple. This tension drove the scientific dialogue, creating a dramatic backdrop for the discoveries. Astronomers were not just measuring light, they were witnessing a cosmic surprise unfolding billions of years in the past, a universe more advanced than their own simulations had allowed. The community also began to examine the candidate galaxies individually, analyzing each one for its mass, brightness, and chemical composition. Every discovery fueled discussions about timing, structure, and evolution. Some galaxies appeared so massive that they could not have formed in the expected 300–400 million years without extraordinary efficiency. Others displayed metal content that implied previous generations of stars had already lived and died even earlier, adding another layer of complexity. Each galaxy became a case study, a focal point for debate, and a challenge to accepted models. Journals began publishing papers discussing possible explanations, from accelerated star formation to early mergers, all while maintaining caution about drawing conclusions that might overturn the Big Bang itself. The discoveries forced a re-examination of how quickly the early universe could build massive, luminous, and chemically complex galaxies. Redshift and lookback time explained. When the James Webb Space Telescope first turned its gaze to the deep universe, it looked not just across space, but also back in time. Every star, every galaxy, every glimmer of light that JWST observes is a message from the past. Light travels at a fixed speed, and the distances between us and these galaxies are so enormous that the light takes billions of years to reach the telescope. This means that JWST does not see these galaxies as they are now, but as they were billions of years ago. The universe itself has been expanding ever since the Big Bang, stretching the light along with space as it grows. This stretching changes the color of the light, moving it toward the red end of the spectrum. Astronomers call this phenomenon redshift. The higher the redshift, the further away and older the galaxy is. JWST measures redshift to calculate how long the light has been traveling and, in turn, how far back in time we are looking. Redshift is not just a number, it is a cosmic clock, telling scientists the age of the light, the distance of the galaxy, and the place it occupies in the history of the universe. Redshift is central to how JWST understands the early universe. Galaxies at redshift Z tilde, 13 to 15 for example, are seen as they existed only 300 to 400 million years after the Big Bang. At this moment in cosmic history, the universe was less than 3% of its current age. The light captured by JWST has traveled for more than 13 billion years, crossing vast stretches of space that have been expanding continuously. This makes each observation both a look into the distant past and a measure of cosmic scale. By measuring the degree to which light is stretched, astronomers can calculate the lookback time, the number of years the light has been traveling before reaching the telescope. Lookback time and redshift are intimately linked, forming the timeline that allows scientists to place galaxies along the story of cosmic evolution. With these tools, JWST transforms distant points of light into markers of the universe's history, revealing galaxies not as they are today, but as they existed when the cosmos was still a fraction of a billion years old. The process of measuring redshift combines precision and ingenuity. JWST's instruments capture the spectrum of each galaxy, breaking the light into its component colors. Absorption lines, caused by elements within stars and gas clouds, shift toward red as the universe expands. By calculating this shift, astronomers determine the galaxy's redshift, and from that, its lookback time. This method is highly effective for distant, early galaxies, whose light has been stretched into the infrared by billions of years of expansion. The telescope's ability to measure these tiny changes allows scientists to pinpoint when a galaxy formed and how it fits into the timeline of cosmic evolution. Redshift, then, is both a ruler and a clock, a way to measure distance and a way to measure age. Without it, JWST could see the light, but not understand the story behind it, leaving the early universe as an unexplored mystery. Redshift and lookback time also give context to JWST's discoveries of galaxies that seem too early and too massive. Knowing exactly when these galaxies existed allows astronomers to compare them with theoretical models, testing predictions about how quickly stars and galaxies could form. If a galaxy exists at redshift Z tilde 14, for instance, it must have formed and grown to its observed size within only a few 100 million years. These time constraints make the observations remarkable. The light shows not just a galaxy in the distance, but a cosmic system that assembled faster than expected, challenging assumptions about the early universe. By tying redshift to lookback time, JWST turns each observation into a probe of cosmic history, revealing not just what galaxies look like, but when and how they formed. The concept of lookback time makes the universe tangible. It is one thing to hear that a galaxy is 13 billion light-years away, and another to realize that JWST is seeing it as it existed in the first few 100 million years after the Big Bang. The light is ancient, but it carries the story of formation, star birth, and early chemical enrichment. Every photon captured by JWST tells a tale that bridges time, connecting the infancy of the universe with our own moment in history. Redshift allows astronomers to decode this message, turning colors and spectra into ages and distances. It transforms images into timelines, revealing the pace of cosmic evolution and allowing scientists to test their expectations against what the universe actually produced. Redshift also allows astronomers to identify extreme objects, the galaxies, that push the limits of theory. By measuring the redshift precisely, JWST can determine which galaxies are seen at the very edge of the observable universe. These extreme redshift galaxies are among the first ever to form, appearing only a few 100 million years after the Big Bang. Their light has traveled almost the entire age of the universe to reach us, providing a direct view of cosmic dawn. Galaxy formation models versus JWST observations. For decades, scientists have relied on a framework called lambda CDM, or LCDM, to explain how the universe formed its structures. This model, based on the Big Bang, dark matter, and dark energy, has guided astronomers in predicting how galaxies should grow and evolve over time. Lambda CDM assumes that the universe started in a hot, dense state and then expanded, with matter slowly clumping together under gravity. Small fluctuations in density led to the gradual buildup of stars, gas, and eventually galaxies. According to this model, galaxies form in a hierarchical way. Small clumps of stars and gas merge over hundreds of millions of years to create larger, more massive galaxies. The first galaxies were expected to be faint, rare, and primitive, slowly growing as they pulled in more gas and merged with neighbors. The predictions were clear. By 300 to 400 million years after the Big Bang, the universe should only contain tiny dim galaxies, barely beginning to form stars. Only after hundreds of millions more years would the first massive galaxies appear. This was the story astronomers had told for decades. Hierarchical structure formation is at the core of lambda CDM. In this picture, galaxies are built like Lego towers, small blocks merging into larger structures over time. First come the smallest galaxies, tiny systems containing a few million stars at most. Over hundreds of millions of years, these small galaxies collide and combine, slowly forming larger systems. Gas clouds within these galaxies cool, collapse, and give birth to new stars. Gravity pulls clumps together, and the universe gradually grows from simple beginnings into the complex web of galaxies we see today. Hierarchical formation also predicts that early galaxies would have low mass, low brightness, and minimal chemical enrichment. Heavy elements, metals formed in stars, should only appear later, after many generations of star formation. This step-by-step growth has been the backbone of theoretical cosmology for decades, providing a timeline for how the universe transforms from a near-empty expanse into a rich, structured cosmos. JWST's observations, however, paint a very different picture. The telescope's first deep-field images revealed galaxies that are far too early and far too massive to fit comfortably into the hierarchical model. Candidate galaxies at redshift Z(1315), seen only 300 to 400 million years after the Big Bang, are already enormous. They shine brightly, contain billions of stars, and appear well-structured. The existence of such massive systems so early is unexpected because lambda CDM predicts that assembling this much mass should take longer. According to the model, these galaxies should still be tiny clumps struggling to form their first stars. Instead, JWST shows galaxies that seem fully grown, defying the slow step-by-step growth process that hierarchical structure formation suggests. The discovery is startling because it challenges a central assumption, that early galaxies must be small and primitive. The gap between theory and observation has led to intense scrutiny. Astronomers are now asking how the universe could produce massive galaxies so quickly. If hierarchical formation is correct, then something must be happening in the early universe that accelerates growth, allowing stars and gas to gather faster than predicted. JWST's data shows that galaxy formation may not be as slow and gradual as models suggest. Perhaps gas cools and collapses more efficiently than expected, or early star formation operates under conditions that favor rapid mass buildup. These observations force scientists to reconsider the rules of early cosmic evolution and rethink the timeline of galaxy assembly. The telescope has revealed that the universe, far from being a slow and careful builder, may have been surprisingly efficient and ambitious in forming its first grand structures. Lambda CDM also predicts limits on the maximum mass galaxies can reach at specific times. These limits are based on calculations of how quickly matter can collapse under gravity and how long it takes for stars to form. When JWST found galaxies exceeding these masses only 300 to 400 million years after the Big Bang, it caused immediate excitement and concern. Astronomers realized that the mass and brightness of these early galaxies were inconsistent with standard predictions. If these galaxies are as massive as measurements suggest, then the models either underestimate the speed of star formation or fail to account for some other factor that drives rapid growth. The hierarchical model assumes time is a limiting factor, yet JWST shows that the universe somehow found a way to produce massive luminous galaxies much earlier than anyone expected. The implications go beyond simple numbers. Hierarchical formation also predicts a gradual buildup of metals in galaxies. Small primitive galaxies merge over time, and heavy elements are produced slowly as successive generations of stars live and die. JWST's early observations challenge this assumption as well, because the galaxies seen at extreme redshifts already appear to contain metals. Their high mass, combined with unexpected chemical enrichment, suggests that star formation was not only fast, but also efficient at producing heavy elements. This means that early galaxies were not only assembling quickly, but also maturing chemically at a rate that theoretical models had not predicted. The hierarchical model, which relies on gradual growth and enrichment, struggles to explain how such complex systems could exist so early in cosmic history. The surprise is even more dramatic when considering the density of galaxies in JWST's deep field images. Lambda CDM predicts that early galaxies should be rare, scattered sparsely across space. Yet the telescope reveals numerous massive galaxies packed within a single field of view, each glowing brightly, each massive enough to challenge existing models. This abundance suggests that the early universe was far more active than predicted. The process of hierarchical assembly may not have been as slow and staggered as previously thought. Instead, the early universe may have been a hub of rapid star formation, efficient gas collapse, and accelerated mergers, producing galaxies at a pace far beyond theoretical expectations. These observations have ignited a wave of research aimed at reconciling theory with evidence. Scientists are testing variations of Lambda CDM, adjusting parameters to see if more rapid growth can be accommodated. Others are exploring alternative models, considering ways the universe could produce massive early galaxies without violating the principles of the Big Bang. Some suggest that our understanding of dark matter, which governs how galaxies form and cluster, may need refinement. Others examine whether the efficiency of star formation in the early universe has been underestimated. JWST's findings have turned galaxy formation models into a central focus of modern cosmology, forcing researchers to rethink long-held assumptions. The tension between hierarchical structure formation and JWST observations also highlights the limitations of previous telescopes. Hubble could detect early galaxies, but only the brightest and closest ones. Many faint, distant galaxies remained invisible. JWST, with its larger mirror and infrared vision, now reveals galaxies that Hubble could not detect. This improved sensitivity allows astronomers to see galaxies at redshifts previously inaccessible, directly testing the predictions of hierarchical formation. The result is a confrontation between theory and observation at the most fundamental level, galaxies forming faster, larger, and brighter than the models allow. JWST's discoveries show that hierarchical structure formation may not fully capture the story of early galaxy assembly. The model remains a valuable framework, explaining much of what we see in the nearby universe, but it struggles to explain the rapid emergence of massive galaxies so soon after the Big Bang. Each new observation of an early massive galaxy adds weight to the idea that the universe is more efficient at creating stars and galaxies than the textbooks suggest. This does not mean the model is entirely wrong, but it does indicate that revisions are needed, whether in the rate of star formation, the role of mergers, or the physics governing early galaxy evolution. JWST has provided the data needed to challenge, refine, and expand our understanding of the first cosmic structures. The metallicity paradox. One of the most surprising discoveries from JWST is the presence of heavy elements or metals in galaxies seen only a few hundred million years after the Big Bang. In astronomy, metals are any elements heavier than hydrogen and helium, created inside stars through nuclear fusion. Stars burn hydrogen and helium to produce heavier elements like carbon, oxygen, and iron. These metals are released into space when stars die, either through gentle winds or violent explosions called supernovae. The process of creating metals and enriching the surrounding gas takes time. According to models, the first galaxies should have contained mostly hydrogen and helium, with very few metals. Early stars, called population 3 stars, were expected to form from nearly pure hydrogen and helium, shining brightly but briefly before enriching the universe gradually. The presence of metals in galaxies observed by JWST challenges this simple picture. JWST's observations show galaxies that are already chemically enriched at redshifts Z(13 to 15, only 300 to 400 million years after the Big Bang. This is astonishing because producing metals requires multiple generations of stars. First, stars must form, burn, and die, releasing metals into surrounding gas. That gas then needs to collapse into new stars, repeating the cycle. Each step takes time, and in the early universe, this process was thought to be slow and gradual. Yet, JWST shows galaxies that are massive, bright, and already enriched with metals, suggesting that star formation and chemical evolution occurred at a pace much faster than expected. These galaxies contain heavy elements in quantities that models had predicted would appear much later, creating a puzzle that astronomers call the metallicity paradox. The metallicity paradox forces scientists to rethink the timeline of nucleosynthesis, the process of creating elements inside stars. Traditional models assume that the first stars take tens of millions of years to live and die. Their supernovae seed the surrounding gas with metals, which then form new stars in a gradual build-up. JWST's early galaxies appear to have gone through this cycle rapidly, in a fraction of the time models predicted. The presence of metals so early implies that star formation must have been extremely efficient, that the first stars formed quickly, lived briefly but intensely, and enriched their surroundings with extraordinary speed. The universe, it seems, was accelerating chemical evolution far beyond what theory allowed. This paradox is also tied to galaxy mass. Massive galaxies observed by JWST not only have lots of stars but also show high metal content throughout. Metals are indicators of prior generations of stars, so these massive galaxies must have formed stars quickly and repeatedly. Each generation contributes to the metal content, and doing this in just a few hundred million years pushes the limits of our understanding. The data suggests that the early universe was capable of producing stars in rapid succession, creating galaxies that were chemically mature, while theory suggested they should still be primitive. These enriched galaxies are bright, massive, and complex, revealing a universe far more efficient at creating heavy elements than textbooks predicted. The metallicity paradox also raises questions about the first stars. Population 3 stars, composed almost entirely of hydrogen and helium, were thought to dominate the earliest galaxies. They were massive, short-lived, and responsible for producing the first metals. JWST's observations imply that these stars must have formed, lived, and died even earlier than 300 and 400 million years after the Big Bang to account for the metals seen in galaxies at Z(1315). This suggests an incredibly rapid cycle of star birth and death in the first galaxies, faster than simulations have ever predicted. The paradox is that these early galaxies already show the chemical fingerprints of multiple generations of stars, challenging the assumptions about how quickly stars can form and how efficiently they can enrich the universe. Chemical enrichment also affects how galaxies evolve. Metals influence cooling, which affects how gas collapses to form new stars. Higher metal content allows gas to cool faster, leading to faster star formation and more rapid galaxy growth. The unexpectedly high metallicity in early JWST galaxies could explain their rapid assembly, as enriched gas collapses more efficiently than pristine hydrogen and helium. Yet even with this feedback mechanism, producing the observed metal content so early remains a challenge for existing models. The paradox lies in the timing. The universe seems to have accelerated chemical evolution and galaxy assembly simultaneously, leaving theorists scrambling to explain how such complex systems formed so quickly. JWST's metallicity measurements rely on infrared spectroscopy. The telescope can detect light from distant galaxies that has been stretched into the infrared by cosmic expansion. Spectral lines reveal the presence of metals and allow astronomers to quantify chemical abundances. The surprising results show that galaxies at redshift Z-1315 have metallicities far higher than expected for their age. This is a direct, observable challenge to nucleosynthesis timelines, providing evidence that the early universe was chemically richer and more evolved than previously thought. Each spectrum tells a story of rapid star formation, multiple stellar generations, and early enrichment, painting a picture of a universe moving faster than models anticipated. The metallicity paradox also affects our understanding of cosmic evolution. Metals drive the formation of planets, influence the life cycle of stars, and shape the interstellar medium. Finding metals so early implies that the building blocks for complex chemistry, and eventually life, were in place much sooner than theories suggested. JWST is revealing that the early universe was not only rapidly forming stars and galaxies, but also creating the chemical ingredients for more complex structures far earlier than predicted. The presence of metals in these early galaxies provides a new lens through which to view the evolution of the cosmos, one that challenges assumptions about timing, efficiency, and the pace of chemical enrichment. Infrared imaging, seeing what Hubble couldn't. The James Webb Space Telescope was built to see the universe in a way no telescope before it could. Unlike Hubble, which sees mostly visible and ultraviolet light, JWST sees primarily in infrared. This is crucial because light from the earliest galaxies has traveled for more than 13 billion years, and as it moves through the expanding universe, it stretches. This stretching shifts the light from visible wavelengths into the infrared. Hubble, for all its power, could only detect the brightest, closest galaxies in the visible spectrum. The earliest, most distant galaxies were too faint and too redshifted to be captured by its instruments. JWST, with its infrared vision, changes everything. It can detect this stretched light, revealing galaxies that Hubble simply could not see. Every photon captured by JWST is a messenger from the dawn of the universe, carrying information about stars, gas, and structures that had remained hidden for billions of years. Infrared imaging is more than just a different color of light. It's a key that unlocks the early universe. Because the universe has been expanding, light from galaxies at redshifts Z-1315 has been stretched so far that it no longer reaches the visible spectrum. JWST's infrared detectors, combined with its massive gold-coated mirror, allow astronomers to capture this light in exquisite detail. This capability opens a window to a time when galaxies were forming their first stars, when chemical enrichment was just beginning, and when massive, surprisingly mature galaxies emerged much earlier than theory predicted. Without infrared imaging, these galaxies would remain invisible, hidden behind the limits of previous technology. Infrared is the telescope's superpower, letting humanity witness events that occurred when the universe was less than a few % of its current age. The design of JWST makes this infrared vision possible. Its sunshield, a tennis court-sized structure, blocks heat from the sun, Earth, and Moon, keeping the telescope cold enough to detect faint infrared signals. Any warmth from the telescope itself would overwhelm the delicate light from distant galaxies. This extreme cooling allows JWST to measure the infrared glow of galaxies billions of light years away, capturing both their structure and chemical signatures. By imaging in the infrared, JWST can observe light that has been traveling for more than 13 billion years, stretched and dimmed by cosmic expansion. This allows astronomers to study galaxies at the very edge of the observable universe, testing theories of galaxy formation, chemical evolution, and the earliest cosmic structures. Infrared imaging also enables JWST to see through cosmic dust. Many galaxies, even relatively nearby ones, are filled with gas and dust that absorb visible light. This dust hides stars and structures from telescopes like Hubble. Infrared light, however, passes through dust more easily, revealing stars and star-forming regions that would otherwise remain invisible. In the early universe, dust can form quickly in the deaths of massive stars, and infrared imaging becomes essential to see these nascent galaxies clearly. JWST's ability to penetrate dust provides a more complete picture of galaxy formation, showing both the bright cores and the hidden structures that contribute to rapid star formation and early chemical enrichment. The difference between what Hubble could see and what JWST reveals is striking. Hubble's deep field images gave humanity the first glimpses of the distant universe, showing faint smudges of light and small primitive galaxies. These images inspired decades of research, but they were only the tip of the iceberg. JWST, by observing in infrared, reveals galaxies that are larger, brighter, and more chemically evolved than those in Hubble's deep fields. Galaxies that Hubble could not detect now appear in stunning clarity, their light showing mass, structure, and chemical composition. Infrared imaging turns what was once a blurry hint into a detailed, observable reality. JWST's infrared vision also allows astronomers to measure redshift and metallicity in ways Hubble could not. By capturing infrared spectra, the telescope can detect absorption and emission lines that indicate the presence of heavy elements, star formation rates, and galaxy masses. This is how JWST discovered massive chemically enriched galaxies at redshifts Z-1315. Without infrared imaging, these measurements would be impossible. The combination of long wavelength detection, extreme sensitivity, and high resolution gives astronomers the ability to study the first galaxies in ways that were once unimaginable, revealing both their age and composition. The infrared advantage explains why JWST is rewriting the story of the early universe. Hubble showed a universe that was slowly building galaxies, small and faint, consistent with hierarchical models. JWST, by seeing in infrared, reveals galaxies that are massive, bright, and already chemically complex at a fraction of a billion years after the Big Bang. This difference is not just technical, it is transformational. Infrared imaging provides the proof that the early universe was more active and more evolved than previously thought. It allows scientists to see the full range of galaxy formation, from the tiniest clumps to the first massive systems, offering a complete picture that Hubble could only hint at. Could this prove the Big Bang wrong? The James Webb Space Telescope has opened a window to the early universe, revealing galaxies that appear far too massive, too bright, and chemically mature to exist only 300 to 400 million years after the Big Bang. For astronomers and cosmologists, these discoveries are nothing short of shocking. The first question on everyone's mind is simple, yet profound. Could this mean the Big Bang theory itself is flawed? The Big Bang has been the cornerstone of modern cosmology for nearly a century. It explains how the universe expanded from a hot, dense state roughly 13.8 billion years ago, and has successfully predicted phenomena like the cosmic microwave background, the relative abundance of elements, and the large-scale structure of galaxies. But the early JWST data challenges one of its central assumptions, the timeline for how quickly galaxies could form and evolve. These massive, chemically rich galaxies seem to appear almost instantly after the universe's birth, leaving scientists questioning whether the standard model is missing something fundamental. If these observations are confirmed, astronomers may need to confront the possibility that our understanding of the early universe is incomplete. Perhaps the Big Bang itself is not wrong, but the models that predict how matter clumps into stars and galaxies need dramatic revision. In standard models, the first galaxies were expected to be small, faint, and primitive. Hierarchical growth would gradually assemble larger galaxies over hundreds of millions of years. JWST, however, shows galaxies that are already enormous and well-formed at times when, according to theory, the universe should still have been in its infancy, struggling to form its first stellar structures. The mismatch between observation and expectation is not minor, it is profound. It raises questions about the processes driving star formation, the role of dark matter, and the very pace at which cosmic structures emerged. Some scientists have proposed alternative explanations that could reconcile JWST's findings with the Big Bang framework. One possibility is that star formation in the early universe was far more accelerated than previously thought. Gas could have collapsed into stars faster, generating massive galaxies in a fraction of the expected time. Another hypothesis involves unseen interactions with dark matter. While invisible, dark matter shapes how galaxies form and cluster. If early dark matter behaved differently than current models predict, perhaps clumping more efficiently or triggering faster gas collapse, it could explain the early emergence of massive galaxies. These alternative scenarios are speculative, but they illustrate how JWST's data is pushing cosmologists to consider mechanisms beyond the standard timeline, stretching their models to account for galaxies that should not exist yet. The reactions from expert voices in the field have been a mix of awe, caution, and excitement. Some cosmologists have described the findings as stunning and completely unexpected, emphasizing that the universe is revealing behaviors that were not predicted by even the most sophisticated simulations. Others urge restraint, noting that while the data challenges models, it does not automatically invalidate the Big Bang itself. This is not a contradiction of the Big Bang, one cosmologist explained. It's a challenge to our assumptions about how matter organizes into galaxies in the early universe. Another expert remarked, "For the first time, the universe is telling us a story we weren't prepared for. We have to listen carefully and let the data guide us." These voices underscore the tension between theory and observation. JWST is showing galaxies that defy expectations, but interpretation requires caution and rigorous confirmation. Part of the caution comes from the way these early galaxies are measured. Many of JWST's distant galaxy candidates rely on photometric redshifts calculated from the brightness of light in multiple infrared filters. While effective for identifying potential high-redshift galaxies, photometric estimates can sometimes be misleading. Spectroscopic confirmation, which directly measures the absorption and emission lines of elements in the galaxy, is necessary to verify distances, masses, and chemical composition. Until these confirmations are complete, astronomers treat the early findings as preliminary, though highly intriguing. The excitement comes not just from the potential challenge to theory, but from the unprecedented view JWST provides, a direct glimpse of galaxies forming at the very edge of cosmic history, revealing the universe in a way no previous telescope could. JWST's discoveries blur the line between data contradicting theory and data demanding better models. In some cases, observations may indicate gaps in our understanding rather than outright flaws in fundamental theory. For example, the existence of massive early galaxies could point to star formation efficiencies that have been underestimated, or to physical processes in the early universe that simulations have yet to include. Models of cosmic evolution are only as good as the assumptions they make about gas dynamics, feedback from star formation, dark matter behavior, and chemical enrichment. JWST's findings force a re-evaluation of these assumptions, showing that the universe may have been far more dynamic, productive, and chemically mature than previously imagined. With massive galaxies glowing brightly, chemically enriched and structured, while according to our textbooks, it should still have been in the womb. The images and spectra from JWST evoke a sense of wonder and urgency. We are seeing the universe's formative years played out in real time across billions of light years, a drama of cosmic creation that unfolds faster and more efficiently than our models predicted. Each new galaxy revealed is a character in this unfolding story, showing rapid growth, chemical richness, and surprising mass, and each challenges astronomers to revise the narrative of cosmic evolution. Even as JWST opens this window, the scientific community approaches the findings with a measured approach. While the telescope's early data is transformative, astronomers know that extraordinary claims require extraordinary evidence. The final verdict will come after extensive spectroscopic follow-up, careful modeling, and repeated observations. Yet even at this early stage, it is clear that the universe is teaching us something new, something unexpected, and something profound. It is a lesson in humility. The cosmos is not bound by the limits of our imagination or the assumptions of our models. The galaxies JWST reveals are both beautiful and challenging, forcing humanity to confront the universe's early years in ways we never anticipated. It is a confrontation between expectation and reality, theory and observation, prediction and discovery. For decades, cosmologists have worked within the framework of lambda CDM, relying on simulations and models to describe the pace of galaxy formation. JWST now shows that reality can exceed imagination, that the universe may assemble massive galaxies faster than the rules we devised allow, and that our understanding of the cosmos, while powerful, is still incomplete. The telescope's infrared eyes have pierced the darkness of the early universe, revealing a cosmos that is more complex, more evolved, and more surprising than we dared hope. JWST's early results spark debate, excitement, and caution simultaneously. The implications reach beyond galaxies, touching the foundations of cosmology itself. Are these galaxies signaling a flaw in the Big Bang, or are they evidence that our galaxy formation models are incomplete? Could unseen processes, perhaps involving dark matter or accelerated star formation, be at play? While the answers are not yet certain, the questions themselves are transformative. JWST has provided the data that allows scientists to ask questions they could not have formulated before, forcing a re-evaluation of what we know about the universe's first few 100 million years. The early galaxy clusters. The James Webb Space Telescope has detected groupings of galaxies far earlier than expected, challenging previous assumptions about how quickly the universe could form large structures. Standard models based on the Big Bang predict that the first galaxies formed as small, faint, and isolated objects, slowly merging over hundreds of millions of years. Large-scale structures, such as clusters of galaxies held together by gravity, were expected to appear only after the universe had matured and enough mass had accumulated. The detection of multiple galaxies forming clusters just 300 to 400 million years after the Big Bang shows that the early universe was capable of producing massive structures much faster than theory predicted. These clusters are not simply random alignments. Their proximity and number indicate that gravitational forces were able to bring galaxies together very early, providing evidence that matter could organize quickly into significant structures. The physical properties of these early clusters are striking. JWST shows that member galaxies are massive and luminous, with substantial stellar masses, indicating that they had already formed many stars in a very short time. This is unexpected, because models predicted that galaxies at such early times would be smaller, less developed, and relatively primitive in both size and mass. The clusters contain multiple galaxies within a single region, suggesting that star formation and galaxy assembly were operating efficiently. Observations reveal that these galaxies already have internal structures, including dense cores and regions with high star formation activity. These findings indicate that galaxies did not just exist in isolation, but interacted with their surroundings, with gravity accelerating their growth and assembly into clusters. Infrared imaging is critical for detecting these early clusters. Light from the most distant galaxies has been traveling for over 13 billion years and has been stretched into the infrared due to the expansion of the universe. Hubble, observing primarily in visible light, could detect only the brightest, closest galaxies, missing the bulk of early galaxy clusters. JWST, with its infrared capabilities, is able to observe these faint, red-shifted objects, confirming their existence and mapping their spatial relationships. This allows astronomers to identify groupings of galaxies, measure their distances, and determine their masses, showing that clusters were already forming much earlier than theory suggested. The telescope's sensitivity and resolution in the infrared spectrum make it possible to detect not only individual galaxies, but also the dense regions where multiple galaxies exist together. The presence of these early clusters has implications for our understanding of dark matter, the invisible component of the universe that drives gravitational assembly. Clusters require significant amounts of mass to remain bound, most of which is thought to be dark matter. The fact that JWST observes tightly grouped massive galaxies at high redshifts suggests that dark matter had already begun to form concentrated structures capable of drawing in gas and forming galaxies rapidly. This challenges assumptions about the timing of dark matter collapse and the rate at which gravitational structures could develop in the early universe. It also implies that the first galaxies could form and grow more quickly than predicted by models that did not account for these early concentrations of dark matter. Observations of early galaxy clusters also reveal that these galaxies were chemically enriched. Despite their young age, many show signs of metals produced by prior generations of stars. This indicates that star formation in these galaxies must have been rapid and continuous, providing enough time for multiple cycles of star birth and death to enrich the surrounding gas. The detection of metals in clustered galaxies further challenges the notion that early galaxies were primitive and simple, showing instead that chemical evolution occurred faster than previously expected. The combination of high mass, dense clustering, and early enrichment demonstrates that the processes responsible for galaxy formation, interaction, and growth were operating at peak efficiency in the early universe. Galaxy clusters at high redshift also provide insight into how large-scale structure evolves over time. In the local universe, clusters are common, with hundreds or thousands of galaxies bound together. The early detection of clusters shows that the seeds of these structures were already present within the first few 100 million years. This indicates that the hierarchical formation process, where small galaxies merge to form larger ones, may have been accelerated in the early universe. The proximity of massive galaxies within clusters suggests that gas cooling, star formation, and gravitational interactions all occurred simultaneously, resulting in structures that formed far earlier than expected. These findings force a re-examination of the timeline for galaxy assembly and highlight the efficiency of early cosmic processes. The measurement of galaxy properties within these clusters relies on both photometry and spectroscopy. Infrared photometric data from JWST allows astronomers to estimate the distances and redshifts of galaxies, confirming that they are part of the same high redshift group. Spectroscopic observations can provide more precise measurements of mass, star formation rates, and chemical composition. Early analysis indicates that these clusters contain galaxies with masses much higher than predicted by models, and their star formation activity is already significant. This suggests that gas accretion, cooling, and star formation occurred much faster in clustered environments than in isolated galaxies. These observations are important for testing models of early universe physics and understanding how matter organizes under the influence of gravity. Early galaxy clusters also provide a benchmark for testing cosmological simulations. Models based on lambda CDM predict the number density, mass distribution, and growth rate of galaxies over cosmic time. JWST's detection of massive clusters at very high redshift suggests that simulations may underestimate the speed and efficiency of galaxy assembly. To reconcile observations with theory, models may need to account for accelerated gas accretion, rapid star formation, and early dark matter collapse. These clusters offer an opportunity to refine predictions, adjust assumptions, and improve our understanding of how the universe built its first large-scale structures. Finally, the early galaxy clusters identified by JWST represent a shift in our understanding of the pace of structure formation. Previously, the universe's first few 100 million years were thought to be a period of gradual growth and slow organization. JWST shows that this was not the case. The universe was able to produce massive galaxies in close proximity, forming clusters that would eventually evolve into the large-scale structures observed in the local universe. These clusters demonstrate that the processes of star formation, chemical enrichment, and gravitational assembly were more efficient and rapid than models predicted. Star formation rates. One of the most surprising findings from the James Webb Space Telescope is how quickly some early galaxies are forming stars. According to standard models of the Big Bang and galaxy formation, the first galaxies should have taken hundreds of millions of years to gather enough gas, cool it, and convert it into stars. Star formation in these galaxies was expected to be slow and steady, with only small numbers of stars forming at any given time. Observations from JWST, however, show that many galaxies are producing stars at rates 10 times higher than predicted. This means that the processes responsible for turning gas into stars were far more efficient in the early universe than theory had suggested. The star formation rates are measured by analyzing the light coming from galaxies, especially in the infrared. Young, massive stars emit intense radiation that heats surrounding gas and dust, which then glows in infrared light. JWST's infrared instruments can detect this glow even for galaxies over 13 billion light-years away. By measuring the brightness and spectrum of the light, astronomers can estimate how many stars are forming per year in a given galaxy. In many of these early galaxies, the measured rates are astonishingly high, sometimes producing hundreds of solar masses of stars every year. For comparison, the Milky Way forms roughly 1 or 2 solar masses of stars per year today. The early galaxies are far more productive than anything expected for such young systems. These elevated star formation rates also challenge the standard hierarchical models of galaxy growth. In lambda CDM cosmology, small galaxies gradually merge over time to form larger systems. Star formation should therefore be limited in the earliest galaxies because they are small, have low mass, and contain only modest amounts of gas. The fact that JWST observes galaxies forming stars at 10 times the predicted rate suggests that the first galaxies had access to large reservoirs of gas, and that the gas could collapse efficiently into stars. This implies that early galaxies were capable of assembling mass and producing stars much faster than previously assumed. The efficiency of star formation in these galaxies raises additional questions about the conditions of the early universe. Gas in the early universe is mostly hydrogen and helium, with few heavy elements, which can make cooling and collapse into stars less efficient. Yet the observations indicate that gas was cooling rapidly and collapsing into stars at extremely high rates. Some galaxies appear to have formed tens of millions of stars within a few 100 million years after the Big Bang. This is much faster than any model predicted and suggests that early galaxy environments may have been conducive to rapid star formation, perhaps due to higher gas densities, faster cooling mechanisms, or interactions within protocluster regions. The presence of early galaxy clusters also likely contributes to these high star formation rates. Galaxies in dense environments experience more interactions and gravitational effects that can compress gas, triggering bursts of star formation. Observing galaxies forming stars at 10 times the expected rate in clustered regions suggests that early interactions played a significant role in accelerating star formation. Gravity may have been more effective at concentrating gas, and feedback mechanisms, such as supernova explosions, may have redistributed material in ways that promoted further star formation. These observations point to a more dynamic and active early universe than previously imagined. High star formation rates also have implications for chemical enrichment. Rapid formation of massive stars produces heavier elements quickly, which are then recycled into the next generation of stars. This process could explain why some early galaxies already contain significant amounts of metals, despite the universe being so young. It also connects directly to JWST's observations of chemically enriched galaxies, suggesting that rapid star formation was a key factor in creating the heavy elements observed in these systems. The faster stars form, the faster chemical enrichment occurs, compressing processes that were expected to take much longer in the early universe. The discovery of galaxies forming stars at 10 times the predicted rate forces a re-evaluation of early galaxy formation models. Previous simulations underestimated the speed at which gas could collapse and turn into stars in the first few 100 million years. JWST shows that early galaxies were capable of much faster growth, forming stars, accumulating mass, and chemically enriching their surroundings far earlier than expected. These findings are consistent across multiple galaxies, suggesting that rapid star formation was not an isolated event but a common feature of the early universe. The result is a picture of a cosmos that is active, efficient, and capable of building complex structures in a fraction of the time predicted by standard models. Dust and gas content. One of the most surprising discoveries from the James Webb Space Telescope is the presence of dust and gas in galaxies that existed only a few 100 million years after the Big Bang. According to traditional cosmology, the early universe was mostly filled with hydrogen and helium, the simplest and lightest elements. Heavier elements such as carbon, oxygen, nitrogen, and metals are produced by stars during their lifetimes and in supernova explosions. These elements then contribute to the formation of dust, which is made up of tiny solid particles of metals and complex molecules. Because the first stars had only recently formed, models predicted that dust would be extremely rare in galaxies at such high redshifts. JWST's observations, however, show a different picture. Early galaxies contain significant amounts of dust, indicating that star formation and chemical enrichment must have already been operating efficiently. Detecting dust and gas in distant galaxies relies on infrared observations. Dust absorbs ultraviolet and visible light from stars and re-emits it as infrared radiation. JWST's infrared instruments can measure this emission, revealing the presence of dust even in galaxies billions of light-years away. These measurements show that the early universe already had complex environments, with interstellar gas and dust spread throughout galaxies. The amount of dust observed in these young galaxies suggests that multiple generations of stars must have formed and died very quickly, producing metals and seeding the interstellar medium. This challenges previous assumptions about the timeline of chemical enrichment in the early universe, implying that the first generations of stars were able to form, evolve, and explode within a few 100 million years. The presence of dust has direct implications for star formation itself. Dust plays an important role in cooling interstellar gas, allowing it to collapse more easily and form new stars. In regions with dust, gas can lose energy more efficiently, increasing the rate of star formation. JWST's observations suggest that early galaxies may have been able to sustain high star formation rates because of the presence of dust. The combination of gas and dust in these galaxies indicates that star formation, chemical enrichment, and dust production were interconnected processes that operated faster than theoretical models predicted. This is consistent with other findings, such as galaxies forming stars at 10 times the expected rate and the early presence of massive galaxy clusters. Gas content in early galaxies is equally important. Hydrogen gas provides the raw material for star formation, and its abundance and distribution determine how quickly galaxies can build stars. JWST's observations show that early galaxies contain large reservoirs of cold gas, sufficient to support rapid star formation over extended periods. The combination of gas and dust suggests that these galaxies were not only forming stars quickly, but also had the material needed to continue forming stars at high rates. This helps explain why galaxies in the early universe appear massive, luminous, and chemically enriched, even at such young ages. Without such abundant gas, the observed levels of star formation and chemical enrichment would be difficult to achieve. The detection of dust also implies that the first stars, known as population 3 stars, must have existed and lived short but intense lives. Population 3 stars are believed to be massive, composed almost entirely of hydrogen and helium, and capable of producing heavy elements during their evolution. When these stars explode as supernovae, they release metals into their surroundings, which then form dust and enrich the interstellar medium. JWST's detection of dust in galaxies only 300 to 400 million years after the Big Bang suggests that these first stars formed rapidly, lived their short lives, and contributed to dust production in a very short time. This is much faster than previous models predicted, which assumed that the first generation of stars would take longer to produce significant amounts of dust. The chemical composition of dust also provides clues about the processes that created it. Observations indicate the presence of carbon, oxygen, and heavier metals, all of which are produced by stellar nucleosynthesis. The fact that such elements are detected in galaxies so early suggests that multiple stellar populations contributed to dust production, with each generation of stars building on the previous one. This early enrichment means that galaxies in the first few 100 million years were already chemically complex, with interstellar media capable of supporting rapid star formation and the development of heavier elements. This complexity contrasts with earlier assumptions that the early universe was chemically simple, composed mostly of hydrogen and helium, with little dust or metals. Infrared spectroscopy from JWST also allows astronomers to measure the properties of gas in these early galaxies. By examining the emission lines of ionized gas, scientists can determine the density, temperature, and chemical composition of the interstellar medium. Observations show that early galaxies not only contain significant amounts of gas and dust, but also that this gas is already enriched with metals, indicating prior stellar activity. The presence of metals in the gas supports the conclusion that star formation and supernova feedback were operating efficiently and rapidly. Gas and dust together provide the environment needed for continuous and accelerated star formation, explaining why early galaxies appear massive and chemically mature. The discovery of dust and gas in early galaxies also impacts models of galaxy evolution. Many theoretical models assumed that early galaxies were simple, gas-rich, and metal-poor. JWST observations show that this is not the case. Early galaxies were already complex systems with both gas and dust, capable of supporting rapid star formation and chemical enrichment. These findings suggest that the processes of galaxy growth, star formation, and chemical evolution were closely linked and far more efficient than previously thought. Models of early galaxy formation may need to be adjusted to account for the rapid production of dust, the efficient recycling of gas, and the early chemical enrichment observed. The spatial distribution of dust within early galaxies is also important. In many cases, dust appears concentrated in the central regions of galaxies, where star formation is most intense. This central concentration of dust may help regulate star formation by cooling gas and promoting the formation of dense star-forming regions. At the same time, dust can absorb and scatter light, affecting the observed brightness and color of galaxies. JWST's infrared measurements allow astronomers to see through this dust, revealing both the star-forming regions and the surrounding enriched gas. This dual observation provides a more complete picture of early galaxy structure and composition, highlighting the role of dust and gas in shaping the evolution of galaxies. Early dust and gas also suggest that feedback mechanisms were already in place in the first galaxies. Supernova and stellar winds from massive stars can distribute metals and dust throughout a galaxy, influencing subsequent star formation. JWST observations indicate that these feedback processes were operating efficiently, helping to enrich the interstellar medium and regulate star formation. The combination of dust, gas, and feedback may explain why early galaxies could form stars at such high rates while maintaining their structural integrity. Without these processes, the observed levels of chemical enrichment and star formation would be difficult to achieve in such a short period of cosmic time. The presence of dust and gas in early galaxies also has implications for observing the distant universe. Dust can obscure light from young stars, making galaxies appear fainter or redder in optical observations. Hubble, observing primarily invisible light, missed many of these dusty galaxies because their light was absorbed and re-emitted in the infrared. JWST's infrared capabilities allow astronomers to detect this re-emitted light, revealing galaxies that were previously invisible. This has expanded our understanding of the number, size, and chemical richness of early galaxies, showing that the universe was more evolved and active than previously thought. Implication: universe matured faster than Big Bang models predict. The observations from the James Webb Space Telescope reveal that the universe developed much faster than standard Big Bang models predicted. For decades, scientists have relied on the lambda CDM model, which describes the universe as starting in a hot, dense state and expanding over time, forming matter slowly and gradually into stars, galaxies, and clusters. According to this model, the first galaxies should have been small, faint, and rare, with large-scale structures forming only after billions of years. The evidence from JWST, however, shows that massive galaxies, dense clusters, and chemically enriched systems existed just 300 to 400 million years after the Big Bang, suggesting that the processes driving cosmic evolution operated far more quickly than expected. The speed of galaxy formation is one of the key pieces of evidence indicating faster maturation. Early galaxies observed by JWST are forming stars at rates up to 10 times higher than predicted. These galaxies are also already chemically enriched, containing metals and dust that could only have been produced by prior generations of stars. The presence of these metals in such young galaxies indicates that star formation, supernova explosions, and chemical enrichment were all operating efficiently in the first few 100 million years. This means that galaxies were not slowly assembling over time. They were already large, active, and chemically complex, far earlier than models assumed. The rapid formation of galaxy clusters reinforces this point. Multiple galaxies observed in close proximity, interacting through gravity and forming dense groupings, show that the early universe was capable of organizing matter into structures much faster than hierarchical models predicted. The presence of early clusters implies that gravitational collapse, gas accumulation, and star formation were accelerated processes, allowing multiple massive galaxies to form and interact in a relatively short time. This rapid assembly challenges the idea that large-scale structures require billions of years to emerge, demonstrating instead that the universe had the conditions and mechanisms to mature quickly. Gas and dust content provides additional evidence for this accelerated maturation. The presence of significant dust in early galaxies indicates that multiple generations of stars had already formed and exploded, enriching the interstellar medium with metals. Similarly, abundant gas allowed for continuous star formation, maintaining high rates and contributing to the rapid growth of galaxies. Combined with the formation of massive galaxy clusters, this evidence shows that the early universe was not chemically simple or inert, but already capable of producing complex systems with significant stellar mass and structural organization. JWST's infrared observations make these discoveries possible by revealing galaxies and structures that were invisible to previous telescopes. By measuring the redshifted light of galaxies billions of light years away, astronomers can determine the age, mass, and composition of these systems. The data consistently shows that galaxies in the early universe are both massive and chemically mature, contradicting the predictions of models that expected slow, gradual growth. This pattern appears across multiple high-redshift galaxies and clusters, indicating that the accelerated maturation of the universe is a general feature rather than an isolated phenomenon. The implications of a faster maturing universe are significant for our understanding of cosmology. If galaxies, clusters, and chemically enriched systems formed far earlier than predicted, the processes that drive star formation, gas accumulation, and chemical enrichment must be more efficient than current models allow. Simulations may need to be updated to account for faster gas cooling, higher rates of star formation, and rapid gravitational assembly. These adjustments could affect our understanding of dark matter distribution, the timeline of the first stars, and the overall growth of cosmic structures. JWST's observations provide the first direct evidence that these processes were operating at peak efficiency in the early universe. This accelerated maturation also affects how we think about the timeline of the universe's evolution. If massive galaxies and clusters existed within the first few 100 million years, it suggests that the first stars must have formed even earlier than previously assumed, producing metals, dust, and energy to drive rapid galaxy growth. The early appearance of chemically enriched galaxies indicates that stellar populations evolved quickly, with multiple generations contributing to the observed complexity. The universe was assembling large, massive systems in a fraction of the time predicted by standard Big Bang models, showing that cosmic evolution was more rapid and dynamic than textbooks suggested. The implications extend to star formation theories. Rapid formation of massive galaxies implies that gas cooling, fragmentation, and collapse into stars occurred more efficiently in the early universe than expected. Feedback processes from supernovae and stellar winds must have operated in a way that both enriched the interstellar medium and allowed continued star formation. These processes, which were previously thought to take hundreds of millions of years, must have been accelerated to produce the observed high star formation rates and chemical enrichment. This points to a universe capable of self-organizing quickly, forming the structures we now see in the first few 100 million years of cosmic history. The presence of massive, chemically enriched galaxies also affects how we interpret observations of the cosmic microwave background and the early universe. Traditional models link the formation of galaxies to the distribution of matter inferred from the CMB, assuming a gradual buildup of structures over billions of years. JWST's discoveries suggest that these early structures were forming much faster, which could require adjustments in our understanding of the relationship between early matter fluctuations and galaxy formation. The universe appears to have been able to convert small initial density fluctuations into large, massive structures very efficiently, contradicting previous assumptions about the pace of cosmic growth. Observing rapid galaxy maturation also highlights the limits of previous telescopes. Hubble could detect individual galaxies at high redshift, but many early massive systems were too faint or obscured to see. JWST, with its infrared vision, detects both massive galaxies and clusters, showing that the early universe was more populated and more chemically complex than previously realized. The data demonstrates that the first few 100 million years were not a slow, quiet period, but a time of rapid assembly, star formation, and chemical enrichment. These observations force astronomers to reconsider the early universe as a fast-developing system, rather than a gradual one. What could be next? The James Webb Space Telescope has opened a window into the earliest stages of the universe, but what comes next is even more significant. Current observations, while groundbreaking, are only the first steps in a much larger scientific campaign aimed at understanding the first 500 million years of cosmic history. JWST is now carrying out extensive spectroscopy programs, which allow astronomers to measure the light from galaxies in far greater detail. Spectroscopy provides precise measurements of redshift, confirming how far away galaxies are and determining their age with much greater accuracy than photometric estimates alone. This is critical because many early galaxies detected by JWST could have uncertain distances based solely on brightness and color. By analyzing the specific wavelengths of light emitted or absorbed by the gas and stars in these galaxies, scientists can determine their chemical composition, star formation rates, and the presence of metals and dust. Spectroscopic campaigns are ongoing, and the data they provide will either reinforce current findings or offer corrections, ensuring that the early picture of the universe is accurate and reliable. Mapping the first 500 million years of cosmic history is another major focus of JWST's ongoing work. These observations aim to chart the timeline of when the first galaxies formed, how they grew, and how star formation accelerated over time. By creating large surveys that cover different regions of the sky, astronomers can identify both isolated galaxies and dense clusters, observing how matter organized in the earliest epochs. The goal is to assemble a detailed map of the young universe, showing how small structures merged into larger ones, how stars produced the first heavy elements, and how dust and gas were distributed across galaxies. This work is essential for testing the limits of the Big Bang model and understanding whether the universe matured faster than standard theory predicts. It also provides context for other surprising JWST observations, such as the presence of massive, chemically enriched galaxies and high star formation rates within just a few 100 million years after the Big Bang. These ongoing campaigns have the potential to trigger paradigm shifts in cosmology. If spectroscopy confirms that massive galaxies, dense clusters, and chemically enriched systems existed so early, then standard models may need significant adjustments. One possibility is that the physics governing the early universe could be more complex than currently assumed. For example, dark matter models, which describe how invisible matter drives the formation and assembly of galaxies, might require modification. If dark matter behaved differently in the first few 100 million years, it could explain why massive galaxies formed so quickly. Similarly, the processes of gas cooling, star formation, and chemical enrichment might be more efficient or accelerated than models predict, meaning that the early universe operated under conditions far more dynamic than previously thought. Alternative cosmologies are also under consideration. While the Big Bang model has been remarkably successful in explaining the overall expansion of the universe and the cosmic microwave background, the existence of early massive galaxies and chemically enriched systems suggests that some aspects of the timeline may need revision. Scientists are exploring whether early acceleration, chaotic gravitational interactions, or previously unknown physical processes could account for the rapid development of structures. These considerations do not necessarily invalidate the Big Bang itself, but they highlight areas where our understanding of cosmic history is incomplete. By testing these possibilities with JWST data, astronomers hope to refine models and develop a more accurate picture of how the universe evolved in its first 500 million years. Scientific caution is essential during this period of discovery. JWST observations are powerful, but they are still preliminary in many cases. Photometric estimates of galaxy distances, while useful for identifying candidates, can be misleading without spectroscopic confirmation. Some early interpretations of galaxy mass, star formation rate, or chemical composition could change once detailed spectral data becomes available. Astronomers are therefore approaching these findings carefully, confirming results and cross-checking with multiple methods. Despite this caution, excitement is high because the potential discoveries are unprecedented. JWST is revealing a universe that is both familiar in its general structure and surprising in its speed of formation and complexity. Each new measurement adds a piece to the puzzle of the early universe, helping scientists understand not just what exists, but how the processes that shaped it operated so efficiently. Beyond individual galaxy observations, JWST's future campaigns will expand into large-scale mapping of cosmic structures. Surveys aim to examine galaxy distributions, cluster formation, and the evolution of star-forming regions over hundreds of millions of years. By studying the density and arrangement of galaxies in the early universe, astronomers can test predictions about hierarchical formation, gravitational collapse, and the role of dark matter in shaping structures. These results will also provide insight into the efficiency of star formation under different conditions, showing whether early galaxies were consistently forming stars at high rates or whether rapid formation was limited to specific environments. This comprehensive approach allows scientists to connect the dots between individual galaxy properties and the broader evolution of the cosmos. The implications of these campaigns extend to our understanding of cosmic chemical evolution. By measuring the abundance of metals in early galaxies, JWST can determine how quickly the first stars produced heavy elements and how these elements were recycled into subsequent generations of stars. Observing dust and metals in galaxies only a few 100 million years after the Big Bang indicates that chemical enrichment was rapid and efficient. Continued spectroscopy and mapping will clarify whether this enrichment was widespread or localized, providing insight into the pace of star formation and the life cycle of early stellar populations. This, in turn, informs models of galaxy growth, gas dynamics, and the role of feedback mechanisms such as supernova explosions and stellar winds. JWST's findings could also influence our understanding of dark matter and its interactions. If galaxies formed more quickly than predicted, it may suggest that dark matter clumped or collapsed earlier, providing the gravitational scaffolding for rapid galaxy assembly. Observations of galaxy clustering, mass distributions, and gas dynamics will test these ideas, helping to refine or challenge current models. Similarly, by comparing the observed distribution of galaxies with simulations, astronomers can evaluate whether dark matter alone is sufficient to explain early structure formation, or whether additional physics, such as interactions with dark energy or novel particle behavior, may be required. Ultimately, ongoing JWST campaigns represent a critical period of exploration and discovery. Each observation contributes to a growing understanding of the early universe, providing direct measurements of star formation rates, chemical enrichment, gas and dust content, and galaxy clustering. Spectroscopic confirmation and mapping of the first 500 million years will either reinforce current models or challenge them, leading to refinements in cosmology and astrophysics. The telescope's sensitivity and resolution allow scientists to probe regimes that were previously inaccessible, opening new windows into the first epochs of galaxy formation and cosmic evolution. The combination of caution and excitement characterizes the scientific community's response to JWST. Researchers acknowledge that initial interpretations may change as more data becomes available, yet the potential for discovery is unprecedented. Every new measurement offers insight into how the universe grew from a nearly uniform cloud of hydrogen and helium into the complex web of galaxies observed today. By confirming distances, measuring compositions, and mapping early structures, JWST will provide the foundation for understanding the universe's first half-billion years in unprecedented detail. In addition to individual observations, collaborative programs are expanding our understanding of early cosmic history. International teams of astronomers are coordinating surveys, sharing data, and comparing JWST findings with other observatories. These efforts ensure that early discoveries are verified and that the broader context of galaxy formation is considered. Combining infrared observations with complementary data, such as radio or X-ray measurements, allows for a more complete picture of early galaxy environments, including gas dynamics, star formation efficiency, and the interplay between galaxies and their surroundings. JWST's future campaigns may also reveal new phenomena that challenge current physics. Early galaxies and clusters could show unexpected distributions, unusual chemical abundances, or unusual interactions, suggesting that the first half-billion years of cosmic history were more complex than assumed. These observations may indicate the need for modifications to standard physics, revisions to dark matter models, or alternative approaches to early universe cosmology. While such shifts are approached carefully, they highlight the transformative potential of JWST data in expanding our understanding of the cosmos. Why this matters for us. The discoveries made by the James Webb Space Telescope are significant not just for scientists, but for everyone because they provide a direct connection to the very earliest chapters of the universe. Observing galaxies that formed only a few 100 million years after the Big Bang allows humanity to witness events that occurred nearly 13.5 billion years ago. For the first time, people are able to see the raw formation of stars, galaxies, and clusters as they were unfolding, giving us a tangible link to the origins of the cosmos. These observations force us to reconsider our place in the universe, not in a speculative sense, but in the literal way that we are able to observe history in progress on a cosmic scale. We are seeing the first systems grow, the first stars ignite, and the first chemical elements spread, all through instruments designed and built here on Earth, bridging the gap between human ingenuity and the vastness of space. The presence of massive, chemically enriched galaxies so early in cosmic history emphasizes that the universe matured faster than we expected. Observing these structures challenges assumptions about the pace of cosmic evolution and highlights the efficiency of processes like star formation, chemical enrichment, and galaxy assembly. For humanity, this realization is profound because it shows that the universe is not a slow, gradual system, but one capable of rapid development and complexity, even in its earlier stages. The data we gather is not abstract. It is a record of the universe performing its earliest work, captured in the light that reaches us across billions of years. Each measurement, each spectral line, each image of distant dust and gas is a snapshot of cosmic activity that we, as humans, can now directly observe and study. JWST itself is a testament to human achievement. The telescope represents decades of research, engineering, and international collaboration. It combines precision optics, a massive sunshield, infrared detectors, and careful orbital placement to achieve sensitivity and resolution that were impossible just a few years ago. This technology allows us to capture light from the first galaxies, measure star formation rates, detect dust and metals, and map early clusters. The fact that we can build instruments capable of observing events billions of light years away is a clear demonstration of human capability and perseverance. In practical terms, JWST is not just a telescope, it is a bridge between human curiosity and the universe itself, translating faint infrared light into information that allows us to reconstruct cosmic history. The ability to observe the first 500 million years of the universe also strengthens our understanding of physical processes. By studying early galaxy formation, we see how stars, dust, gas, and dark matter interacted to produce the first large structures. Observing high star formation rates, chemically enriched galaxies, and early clusters informs models of how matter organizes in the universe, how elements are distributed, and how energy flows through young systems. These observations, while scientific in nature, also offer insight into the conditions that eventually led to the formation of galaxies like our own, including the Milky Way, and ultimately the solar systems and planets that exist today. In this sense, the earliest light we observe with JWST is directly connected to the cosmic environment that allowed life to emerge billions of years later. Another critical aspect is the universality of the findings. The rapid growth of early galaxies, the presence of dust and gas, and the efficiency of star formation are not isolated phenomena. They are consistent across multiple galaxies, clusters, and regions of the sky. This demonstrates that the early universe was not an outlier or a set of anomalies, but followed principles and processes that operated efficiently on a large scale. For humanity, this means that the physical rules governing the universe are robust and predictable, even in extreme conditions, and that we are capable of measuring and understanding them with tools we design ourselves. It also reinforces the idea that human observation can reach to the edges of both space and time, turning what was once speculative into measurable and analyzable data. JWST's findings also show the importance of connecting technology to exploration. Without the instruments and methods developed over decades, we would not have access to this light. The telescope's ability to capture infrared signals from distant galaxies is the result of countless innovations. Mirror coatings, detectors that operate near absolute zero, orbiting far from Earth's thermal noise, and software capable of processing massive datasets. Each of these elements represents humanity extending its capabilities beyond Earth, using engineering to overcome limitations of distance, light absorption, and faint signals. By doing this, we are able to explore regions of the universe that are literally at the edge of visibility and time, connecting human effort directly to the unfolding story of cosmic evolution. The implications of observing these early galaxies extend to our understanding of the universe as a whole. By seeing structures form faster than expected, we gain insight into the nature of matter, energy, and the physical laws that govern them. Observing dust, gas, metals, and star formation rates informs how galaxies evolve over billions of years. Studying clusters and their interactions shows how gravitational processes operate on a cosmic scale. Each discovery allows scientists to refine models, test theories, and identify areas where our understanding is incomplete. In this way, the universe becomes a laboratory, and JWST is the instrument that allows us to experiment by observation, collecting empirical evidence from a time and place we could previously only imagine. JWST allows us to see the universe not as a distant, abstract concept, but as a tangible system with measurable properties. We can identify the first stars, the earliest galaxies, and the processes that led to chemical enrichment and dust formation. Humans aimed to look back in time, using technology to extend our senses to the very edges of the universe, and in doing so, found a universe that was already active, complex, and capable of producing massive structures, dust, and stars within a fraction of its age. JWST has provided the tools to witness this directly, bridging the gap between human capability and the vast expanse of cosmic history. Observing the universe's earliest chapters is now not just a matter of imagination, but of measurement and understanding, grounded in data that humanity itself has gathered, analyzed, and interpreted through innovation, engineering, and relentless curiosity.